So next tutorial will be Patrice and Nicolas from RBN. We will provide very important test results. Let's welcome Patrice and Nicolas.
Yes, so for this presentation, I would like to introduce my colleague Nicolas. Maybe, yes. So he's currently in France for a break, but he followed the operation, the startup and the operation of the demo plant since beginning of May, from the beginning. And he's the mission chief on IFPN side. And for the next week, he will be replaced by Daisy, which is here with us. Before starting, I just would like to thank all people involved in this startup and operation of this unit. It's colleagues from European team, from IFBN, from Total Energy, and also from Chinese team with DBC colleagues and Chiba University students. So thanks a lot, because it's not an easy challenge, but everybody is motivated to reach the target. So now I leave I let the floor to Nicolas, who will show you the primary results which have been obtained on the demo plant for 4 months. So, your microphone. We don't hear you. Your microphone is off. No, the cursor. Your cursor. Okay.
Excuse me.
Okay.
Excuse me. Can you hear me now?
Yes, you can share your screen for the presentation.
Okay. Okay. Thank you, Patrice, for the introduction. So it's my pleasure today to present the preliminary cheers results we had since 4 months of operation with the European and the Chinese teams. So the agenda of today's presentation is as follows. So I will first start with some safety consideration, even if Xime has already talked about it. Then I will talk about mainly the organization and timeline of the operation. Then I will talk about an important step in the startup, which is the oxygen carrier oxidation step. Then I will talk about also an important thing about the CFC technology is the LVAN calibration and the solid circulation in the complete loop. Then I will talk about also some challenges we need to face and about the manhole refractory consideration. And I will finish this presentation with the main achievement which has been done so far and the next plan for the next operation. So about safety consideration, so as Xime has been talked about that, we had a lot of exchanges with the Chinese and European team to review all of the items important for the ensure good security and good operation inside the startup. So at the beginning we listed around 50 items which needed to be done for the startup. So it was quite challenging and quite time consuming. We also performed some on-site safety equipment for workers or operators, and we also done a PID review to compare the things in the reality on site and the panel version of the PID. We had also a lot of many mitigation action, such like leak test, safety valve check, fire extinguishers, cameras, etc. So a lot of action has been done before the unit ready to start. And so I'm also glad to say that no accident happened during the demo plant operation, which is a very good point. So about the organization, so we had daily presence for technical meetings, for meeting for modification, for repairs, a lot of exchanges with the Chinese team go ahead with the operation. It was very helpful to optimize the time we had the startup and the demonstration unit. The organization was split in shift organization to ensure a 24-hour operation during all of the work. So we had 4 teams, A, B, C, D, which were split with 2 people of EU team and 3 people from Chinese team. For the meetings, the communication was mainly in English, and when it was possible, we had some Chinese-English translation when it was mandatory. So the timelines, the main points of the operation of the startup is as follows. So as Neil already talked about, the construction of the demonstration unit started in January 2022. 1 year later, the commissioning of the unit started up in January 2023. And in April 2023, two persons from the EU team, Régis Desranges and Xiaoyu Yang, went on site to help for the commissioning and to start the next discussion about the operation, reviewing the procedure, and etc. In May, the rest of the EU team went on site to finish the commissioning, to help for the commissioning, and also to continue the technical exchanges about the next operation. During May and early of June, we received a lot about the safety review about the startup, and we also had a look on all of the procedure to ensure good operation. And the official date of the startup was the 6th June of 2023, where we started the heating the unit with natural gas in the air reactor and fuel reactor site. During June and July, we performed the Ibenite plug station, which is an important step to continue the operation, especially for the total circulation of the solid. In August, we succeed to achieve a complete solid circulation in the loop. I will come back on this later on the slides. And now we are going to try to reach the CFC mode in the next days and weeks by first ensuring complete circulation at high temperature and then going to switch to the CFC mode. So about the oxygen carrier pre-oxidation step. So the question is, why do we need the pre-oxidation? So this comes from a study performed in IFPN, where we have seen that with a fresh ilmenite, so without any reaction, we could see that if the temperature is high enough, 500 degrees C, there is some risk of agglomerate of ilmenite in the unit. So this is the concern we need to tackle. And to do so, we find a way to treat the oxygen carrier to avoid the agglomeration at the unit. So how we proceed? The ilmenites need to be fluidized at a high temperature, so around 800 degrees C, to avoid the agglomeration happens during the oxygen carrier circulation. Here you have a picture on the left of some ilmenite which has been pre-treated at 800 degrees C. As you can see, you have agglomeration. And on the right, you have some ilmenite which is agglomerated and which has not been pre-treated. And you can see the shape of the agglomeration, the shape of the vessel inside. So that's confirmed that we need to do the tissue treatment before to do the oxygen carrier circulation in the layer. So in total, we were able to oxidize around 75 tons of ilmenite, which is necessary to ensure complete circulation and with sufficient bed levels in each capacity. And also some data to share that during the pre-oxidation step, we can see that the temperature inside the fuel reactor increases because the oxidation step is exothermic. And so, as the treatment has been finished, you can see the temperature decreasing. So this is a clear link of the oxidation occurring in the reactor. So now, before to go further in the slides, I want to briefly talk about the LVAL principle. So, as you maybe already know, due to the high temperature in the CFC technology, conventional mechanical valve cannot be applied, and so that's why we think about the design to ensure the circulation of the solid through this L valve. And this L valve consists of two standpipes, so one vertical standpipe and one horizontal standpipe. And to control, to regulate the solid flow rate in the L valve, you need to control and to regulate the aeration flow rate. So at 1 diameter above the elbow, you need to add some gases, aeration gases. And by changing the aeration flow rate, you will increase the solid flow rate in the L valve. So in fact, you will increase the velocity and increase the solid flow rate. So what you need to retain is that if you increase this aeration flow rate, you will increase the solid flow rate, and if you close the aeration, you will close the valve. So the solid will circulate. So now I will talk about one important step in the demonstration unit, which is the calibration of the L valve. So there is 3 different L valves in our unit, so which are called X101, X102, and X103. So 1, 2, 3. And for this L valve, we were able to do some calibration. So we have a relation between the solid flow rate going through the L valve and the aeration rate, as you can see on this figure. So it's really a key point because the solid flow rate is really important to control the operation in the unit. So this is the kind of calibration curve we can have, and it has been realized at low temperature. For another L valve, so which connects the divided bed to the fuel reactor, we were also able to do a calibration curve by following the bed levels in the divided bed and the fuel reactor over time. So by following this, we are able also to relate the solid flow rate inside the L valve with the aeration flow rate. So this kind of graph we can have. I just want to say an important thing is that the solid flow rate inside the L valve is really impacted by the temperature inside the L valve and the pressure balance in the inlet and the outlet of the valve. This is an important thing we need to be careful because it can impact a lot the calibration. For the last L valve of the unit, right now so far we couldn't perform the calibration because in fact we succeeded to circulate the L valve, but the control of the L valve was very difficult. So that's something we did not expect, and we are now doing some modification to optimize the control of the L valve, and so those modification has already been done, and we are now waiting to do a new calibration in the coming weeks. So now also I have presented the calibration of the L valve. So now I will talk about how to detect any fluid circulation in our unit, because it's not easy to affirm that okay we are able to circulate and from where to where. So here you have a picture of the unit, and I will talk about how do we succeed to evidence the circulation of solid between the divided bed to the air reactor through this L valve X101. So how we detect it's quite easy. In fact, when you start to circulate solid into the unit, you have the pressure drop inside the air reactor which increases. It's what you can see on this plot on the right, the green part. So once you open the L valve, once you put the flow rate in the L valve, you open the valve, you allow the circulation, and so the pressure drop increases and the temperature inside the air reactor decreases. So it's two clear evidences of solid circulation in the air reactor loop. For the second L valve, for the evidence of solid circulation from the DFB to the fuel reactor, it's the same principle. So we open the L valve, and what we can see is that the level in the divided bed and the level in the fuel reactor are changing. So this one is decreasing and this one is increasing. And so by doing so, we know that we have a transfer of solid from the DFB to the fuel reactor thanks to the X102 L valve. So this is also a clear evidence of solid circulation in another part of the unit. Another solid circulation also, which is a key step for the total total circulation of the solid is the transfer of solid from the fuel reactor to the carbon filter through the fuel reactor riser. So we could know we need a minimum velocity in the fuel reactor. So we increase the velocity by increasing the gas velocity. So we increase the gas velocity by increasing the temperature of the fuel reactor compressor flow rate. So by doing so, we start to transport some OC to the fuel reactor riser, and this is what we can see on the plot. You can see the pressure drop inside the fuel reactor increasing, which means that we have solid transported from the fuel reactor to the carbon filter. Additionally, we can see that the temperature inside the carbon filter and the L valve is increasing, which means that some hot OC from the fuel reactor are being transported in the cold capacity. So this is also another evidence of solid circulation in the fuel reactor system part. And finally, to complete the total loop, we also have some evidences of solid circulation between the carbon filter go back to the air reactor. So we complete the entire loop. And how we detect the same thing as before, we open the valve, and what we can see is that the temperature inside the air reactor is decreasing and the pressure drop increasing. So it's the same as for the L valve X101 just before. And so all of these are clear evidences of we succeed to set a complete circulation of solid in the unit, which is a very challenging part of the demonstration unit. So now, so I talked about the main results we had so far from the beginning of the startup. I also want to, it was a long journey for sure, and I also want to talk a little about part of the challenges we needed to face to get this result and to go further into the demonstration units. So one of them was some issues with the manhole refractory of the fuel reactor. So you can see here a picture of the shell of the manhole, which was quite dark. So it means that the protection of the refractory just behind was not there. So in fact, the refractory pulled down to the reactor. So that's something we didn't expect. As you can see here, the temperature of the shell was quite important. So the question is how these pieces of refractories fall down to the reactor. So that's something which we need to understand. And the main hypothesis, the main reason we think is it's about the slugging regime. So what is the slugging regime? This is a specific fluidized bed regime, which is there. We have the specific fluidized bed regime. And this one, usually, in the different applications in the world, you want to avoid this regime. Because in this fluidized regime, you have a lot of vibration. As you can see on the pressure drop measurement over time, there is a lot of fluctuation. And those fluctuations are due to the vibration generated by this specific regime. So to avoid this regime, we need to increase a lot the velocity or to go to a low gas velocity in the fuel reactor. And so this happened because we are now at, we perform the calibration of the circulation of the solid at quite low temperature. And at low temperature, you are in this slugging regime. In nominal conditions, so in the condition of the CSU mode, we will be at a high velocity because we have a high temperature in the fuel reactor, and so we will be able to go into this regime, turbulent regime, where we have no slugging. So in fact, the problem may be due to the low temperature circulation, and by increasing the temperature inside the unit and by doing the complete circulation at high temperature, we should avoid the presence of the slugging regime in the fuel reactor. So, as I said, we had some issues with the refractory inside the manhole, and so I want also to show how could we solve this problem by changing the design. So here is the initial design of the refractory inside the manhole. You can see 4 pieces which avoid some hot gas and solid going to the manhole shell. So the first work which has been done is to change the design, so by switching from 4 parts to 2 parts, and by adding also 1 metal support which was screwed to the manhole shell. So this was the first position we tried, and unfortunately this was not enough, so the slugging regime was again went the pieces in the factory went into the reactor again, so this design wasn't working. And so now, quite recently, we tried another design. So we keep these two pieces inside the manhole, but we add four metal parts which are welded together. So by doing so, we should avoid the two pieces of factory went inside the reactor during the flooding regime. Transition before go to high temperature. So now, I want also to summarize all of the done which has been realized since the beginning of the demonstration unit. So I will talk about the main achievement which has been realized so far since the beginning. So as I already said, no security issues has been noticed during the operation, so it's a very good point. I also want to highlight the fact that we have a constructive collaboration between the European and Chinese teams. We were quite fast to find solution to discuss about next operation, and it was a key point to ensure a good operation and to go further into the CLC demonstration. I also want to thank TBC for their activity and possibility to do some modification, because this is very important work they have done, and I also want to thank them for that. And as Xavier already talked about, we had the chance to do some dissemination of the CHEERS project around the world with 4 films and 1 on CCTV, which is the main channel in China, so it's very interesting. Another achievement is also the utilities. So the utilities were in line with the requirements. So by utilities I mean the burners, the compressors, the water cooling system, which was very good and allowed us to ensure a good operation. One important step, the first step in fact, which is critical, is the oxidation of ilmenite before to do the complete saturation. So we were able to oxidize inside the fuel reactor 70 tons of ilmenite. So it has been done in a very short time, so it's a very good point. I also mentioned that we succeeded to have a complete solid saturation in the unit through the L valve, even if the control of each one of three, so one of the L valve, need to be optimized, and that's why we are now doing some modification to better control the circulation inside the unit. We have also acquired a lot of data, especially for the L valve calibration, which are very precious because this is the first time of an evidence of solid saturation with L valve at this scale, which is the biggest scale in the world. We have precious data about calculation and the calibration of the L valve. And as I just mentioned, we also validate one of the key elements of the CLC technology, which are the L valve calibration, the L valve circulation, and also the carbon filter working. So we need to wait the CLC mode to be sure that we are able to separate the unpaired compound for the oxide carrier. But this is the first validation of some key elements of the CLC technology. And we really want to go further to test them at high temperature. So now we'll talk about the next challenges we will face in the next weeks and months. So as I said, the most challenging part will be to do a complete solid circulation, but at high temperature. So between 800 and 900 degrees Celsius. So this is the next step, next operation we will do. And when we will be able to establish the solid circulation, the complete solid circulation, we will start the L valve calibration, which will be very important for the operation in the CLC mode. We also need to validate that the heat losses are not strong enough to let our thermal CLC being done. And for sure, the next operation will concern also about to do some CLC test by changing the power, so from 2 to 4 megawatts. And to do so, we need to also face some challenges, for example, to switch from air to steam, to do the gasification of the fuel, and also to ensure the good functioning of the automatic loop with the L valve. So, which is also a key step we need to achieve before to do the CLC mode at high temperature. We need also to continue to acquire a lot of data. and also to consolidate what we have already learned at the beginning, so about the complete solid circulation, about the LVAR calibration. All of this needs to be consolidated because it can be used in some models to improve the accuracy of them, so it's a very key point we need to continue working on. And for sure, all of this works done since the beginning, we need to gather them, to have to do a return of experience for a potential wide process book. Yes. So thank you for your attention. So just want to say that it was and also it is still a real pleasure for me to work on this project, and I will continue to work hard to achieve the CLC mode in the next weeks and months. So thank you very much.
Yeah, thanks very much for Nicolas' nice presentation. So next, any question? Yeah, any question, welcome. Okay. Yeah, please.
Thanks for your presentation. I have two questions. In your presentation, you said you consider the pre-oxidation. I don't understand how to do the pre-oxidation. The first question. Now, another question is when you said during the solid circulation, the air reactor and the fuel reactor temperature is increased, and the pressure drop had increased. I want to know the temperature decrease. How much is maybe the fuel reactor or air reactor temperature decrease? Thank you.
You have questions, Nicolas? No.
No, I'm sorry. If you could share with me, if it's possible.
The first question concerns the procedure for the oxidation. If you can
Yes.
just describe in 2-3 words how we do.
Yeah, so the important step in the oxidation is to fluidize the ilmenite at high temperature, so at 11 degrees. Because the fresh ilmenite is not in the fully oxidized level. You know, for the ilmenite, you have such different possibility to oxidize the fuel, and the fresh state of the ilmenite is not fully oxidized. So in fact, what we need to do is to fluidize with air, it's important, at high temperature to do the reaction which allows the ilmenite to be fully oxidized. And to do so, we use the fuel reactor. So we add around 2 or 3 meters better than the fuel reactor, and we heat up the fuel reactor at 800 degrees C and even more in some cases, and we let the ilmenite fluidize during around 1 hour. But you can see here around 1 hour, and it's enough to fully oxidize and to finish the oxidation step. It's how we did to do the oxidation of the ilmenite.
Thank you.
Nicolas, for the second question, when you start the circulation of oxygen carrier from air level to air reactor, the result was the temperature of air reactor decreased while the pressure drop increased. The question is how about the rate? For example, how much temperature will be decreased per minute or per second? How about the pressure drop per minute or per second? Something like this.
I'm not sure if I answered the question. The question is from how much temperature decrease in the air reactor when we had the circulation, right?
Yes, yes.
Yes. So you can see here on this plot, the blue line here is the temperature inside the temperature rate inside the air reactor. So as you can see, the maximum we reach is minus 50 degrees per minute. So it's quite huge. It's because the temperature inside the air valve, the OC inside the valve was quite low, and the temperature inside the air reactor was at around 500 degrees C. So the difference of temperature inside both vessels is quite different. And the maximum we had is around minus 15 degrees C per minute. So it's a really clear evidence of solid circulation.
Right. Yeah. Any other question? Yeah, I have a question for your presentation. If you go to a slide, in that slide there is circulation rate you remember from air reactor to fuel reactor.
This one?
Yeah, this is the air reactor itself. Maybe next for X103. I think so. The calculation
for this one.
The result. There is a picture.
Yeah.
Okay, go back. Go previous slide. Okay. Yes. Just show one shot there. Okay, we can run this slide based on the PDB design. The circulation rate from a fuel reactor to air reactor will be 200 tons per hour. From the PDB, from the data of PDB process design package for European configuration, as I know, the total circulation rate from fuel reactor to air reactor, the maximum circulation rate will be 200 tons per hour. But now you can see your result was about 20 tons per hour. There is 10 times difference between current value with your design value. How do you think about the next step? What kind of measure, what kind of method can be used to increase your circulation rate?
Yeah. So for calibration, that's really at low temperature. So for the fluid circulation in the L valve is really dependent of the temperature and the pressure balance. So when I say it's really relative, so it means that when you increase a little the temperature inside the valve, it increases a lot the fluid flow rate. So we expect that at high temperature we'll be able to have enough to have 100 tons per hour. And when you say 100 tons per hour, it's for the 12 valves, because you have the heat 103 and heat 101. The 12 valves are going into the air reactor. So in each L valve you have 50 tons per hour. And at high temperature, it will be possible to reach 50 tons on each L valve. And even more, because as you can see, it's low temperature. That's why we are doing right now some modification to better control the solid circulation. But it will be possible to reach the target of 100 tons per hour with the sum of the two L valves at high temperature.
Yeah, at high temperature, the gas velocity will be increased a lot. In this case, yeah, you're right. More particle will go into air reactor, but I think some possibility. If more particle go into air reactor, the battle up or the battle inventory of air reactor will be increased very fast in very short time. For example, when at the original time, for example, the pressure drop may be 10 kilopascal. But when you increase the aeration gas velocity, in a very short time, the battle up may be increased to very high pressure drop, maybe 100 or 50 or 60 kilopascal drop in a very short time. But I think this may be a possibility for your configuration if you increase temperature or the gas velocity for aeration available.
Yeah, I understand your concern. You mean that you will have a lot of huge flow rate going to the air reactor. So, but at high temperature, the gas velocity inside the air reactor will be also increasing. So at low temperature, we can achieve 5 meters per second. But at high temperature, we'll be able to achieve 7 or 8 meters per second. And so it will be easier to transport the particles to the cyclone by increasing temperature. So in fact, both effects, temperature, they will increase the solid flow rate, but they will also increase the gas flow rate inside the air reactor. so we'll be able to transport the solid much easier, and so we expect that it will be enough to do the complete solid circulation at high temperature.
Okay, because of limited time, so we will thank very much for your presentation again. Yeah, thank you.
Okay. Thank you.